Morning again, everyone. So my name is Wasim. You may recognize me. I think some of you, I used to train in Nastran, I think 3-4 years ago. And since then, my colleague here, Sid's been training many of you. So I will go through the presentation and Sid in the background will answer any questions during the presentation. And at the end, we should have ample time, hopefully 10 minutes or so for any further questions. So what I recommend and suggest, you may have questions already. So I suggest you put the questions in the questions dialogue and then Sid will keep and answer them as we go along. And if you have any issues with the audio, I'm sure my colleagues Sid and Justina will try to help you with that. But before you can still hear me, Sid, yes?
I can, yeah.
Okay, fantastic. Right, so let's begin. Let me know when you can see my screen, Sid, before I start talking to myself.
Yeah.
Yes, can you see it?
Yeah.
Okay, fantastic. Right, Sid. Okay. Okay, so for some of you who are not aware of my who I am, so I've been working with Symmetry for over 15 years now, and I have sort of experience with different FEA solutions. Primarily, I started my career in the earlys with MSC, some exposure to ANSYS and Algo, which was an independent company which got acquired by Autodesk and then was called Autodesk Simulation. Obviously, it's no more now, so that product has been obsolete. And then, obviously, if you've been in the training courses, I have been authoring some of the Inventor Stress and Nastran books, which most of you will be already have access to them. Okay, so the agenda for today is basically very, very quickly. Some of you may not be using Nastran or Autodesk Simulation or any other upfront simulation, so I just want to briefly give you the benefits of it, and then I will very quickly go into the big myth, how do normal results are correct, and I will try to go through that as slowly as possible. Some of the stuff we have covered in the training courses, so for some of you it may be a refresher's course, and then I will try my best to discuss stress singularities, which is one of the hot topics in any FEA softwares, and then if there's any questions remaining from Sid answering the questions, then we'll go to them as well. Okay, so very quickly, the two most important benefits of upfront simulation is you have the ability to create great products a lot quicker and a lot faster with informed design decisions. And then just being a little bit cheesy, I thought this is a very common phrase, avoid over-engineering. When I speak to many of you, everyone tells me more or less that we over-engineer to basically make sure that nothing goes wrong in the real life. So this is the reason I'm here. But going back through real life examples, you may have recognized this example. Some of you going back 5-6 years ago, this used to be one of the examples in the Inventor Stress book. This is basically a suspension system under a railway bogie. And the example I'm going to use is basically the brown component there is how would one simulate that and the benefits of it. So we'll go first of all and have a look at hand calculations. Many of you still do hand calculations, but the problem with hand calculations is that can be tedious, and also we have to assume the components and details to be very simple. So in this case here, we take the brown component and we remove the middle piece, the middle feature, the lug, and then we do a classical, simple bending moment calculations. You may be able to include the feature as well, but it becomes tedious. So this is the sort of day-to-day activities when people, FE is not a replacement for hand calculations, but it's something that complements it. So you can carry on doing it. A lot of people still use it just to compare the results. But the really beauty of Nastran or any upfront simulation, Inventor Stress as well, is that we have the ability to analyze the features and components with a lot more accuracy. That's the real beauty of it. And the added bonus of Nastran as well, and Inventor Stress and any other FEA software you may be using, is the ability to perform what-if scenarios to be able to create optimum designs. So something like this. This is a one-off. With hand calculations, it's not so simple. But obviously, if you have been using Nastran for a while, you do appreciate it is a very, very comprehensive piece of software. So this is the real benefits of upfront simulation, and you probably already agree to it. You're probably already doing it most of the time. Now, the big myth. So this is a part of my presentation which I did at Autodesk University. Some of the contents you may be familiar with, and hopefully some of them you might learn something new. So these are the sort of questions everybody have in their sort of head, even if you're a seasoned FEA user. Mesh size. What is an ideal mesh size? I wish I knew that. I'd be a rich person if I could, if I knew what mesh size to use always. And then why do we need to run more than one analysis? These questions are not only for Nastran. These are accepted processes used in all FEA softwares. Which analysis results do I use? The first one, the third one, or the second one? And the results are not what I expect to see. So hopefully by the end of the next 35 minutes, it might give you a little bit more exposure where you may have some sort of idea. Now, before I begin, everybody sort of ask me, well, how do I know? Well, the reality is you are all engineers and designers, so you all have an idea of what where the high stress is going to be as you are designing it. So I haven't got a poll, so I'm not sure how this is going to work. So you all have access to the questions. So if you would like to sort of test your skills, there's no price. So I have an example here. A cantilever type example is fixed at the left-hand side. The load is being applied upwards, and then I have 3 scenarios. And where would you expect the high stress to be? So I will give you a minute or so, 30 seconds, if you want to just mention A, B, and C. It just gives an idea to prove me right or wrong, whether you have an idea, if there is a. Has anybody start putting something in, Sid?
Yeah, so we have a few answers there, yeah.
Okay, wait, let me just, let me see. So this is where I think the high stress is going to be, and based on what you see, Sid, what's the most common popular answer?
Seems to be, well, just as you said it, there seems to be a third answer that somebody gave. So
okay, so what's the most popular one there?
Seems to be, well, B seems to be the most popular one.
What's the second option?
Sorry, say that again.
What's the second option? Anyone got C?
C is at the top now. B is second, and A is first.
Okay, so just a bit of tip, right? I should have said this before, guys. Everything I'm saying here is my personal opinions. So a good idea is that you probably get the highest stress nearer the fixing points. Now the reason C is fine, but that's a lot of distance away from the fixing point. So when that tries to bend upwards, because there is the least amount of material here, and that's closer to the constraints, then that basically is what I believe is the high stress. And obviously one way to find out, guys, is when you run the analysis. Okay, so the next one is probably going to be an easy one, because most of you recognize this one. So I have put the answer in there already because I didn't want. This is an example from our training. So it's the first example we do. Probably spend a whole morning on this with Sid. So I put the answer there as A. But let me try the next one and see if that basically gives another idea. Let's try this one, guys. Maybe not so obvious. What I'm trying to prove here is that every engineer has an idea where it may be. Now, you may not choose to do any FEA, but that will not stop you designing the components. So we started getting some ideas in, Sid.
Yeah.
Okay, I'll go pretty quick. So So this is what I come up with. So I think that and the stress value I'm looking at here, guys, and I will go through this in the webinar further on, is I don't look at one miser stress. I normally tend to look at the first principle or tensile stress. So have we got C, maybe A, I don't know.
Yeah, we have a mix of A mostly. So
okay.
We have a C in there as well from a couple of them. So
okay, fantastic. So okay, right, and then the last one, guys. Okay. Just thought it'd be a little bit of fun to get some sort of interaction. And okay. Right. So in this one here, I put B and C because we're pulling it least amount of material. Okay, that's it, yeah?
Yeah, so B or C is mostly what the answer is.
Excellent. So there we go. So I think everybody agrees that yes, we all have an idea of where the FE is going to be. So I hope that was a little bit useful. Right, so the second tip. Now this is probably everyone's more or less aware of it. So what you have to do here is in Nastran, I'm using Nastran as an example because I think many of you here are Nastran users. So we run a first analysis, then we run a second analysis with a different mesh size. And typically, when I used to do training a little while back, I used to say to everybody is half the size of the mesh every time you change it. So if you start from 3, make it 1.5, and then make 31 at 0.75. And in some cases, you may want to do a fourth mesh, but 3 minimum. And the idea is what you're looking for is the stress results difference. Now, for your own benefit, there is no difference in displacement results. So if you're interested in looking at the displacement results, then one analysis is more than sufficient because displacement results do not tend to change as you change the mesh. It's primarily the stress. Now, what I tend to do here, this is my own personal preference, is that I don't compare the last two results. This one is 10% is the magic number. It's a de facto value used and accepted by many FEs in the world. If a result is within 10%, then you can assume it has converged. But I go one step further and I look at the first and third analyses. It makes me feel more comfortable. Now, for this to work, then do not use a default mesh when you do the first one. Try to reduce the mesh size to a reasonable value. Don't make it too small because you're going to split it 3 times. So start with a mesh size which you feel comfortable and then compare the first and third in an ideal world. But second and third is also fine. Now, split faces is my favorite Inventor feature, where if you have an idea, which we sort of prove to some degree, then I would suggest that you go and split the faces in wherever you expect high stresses. Using the split face, split tool commands. And the idea is that it gives you the ability to put a smaller mesh size in there, and by avoiding trying to mesh everything. So you can't tell pretty clearly from here, but this is the global mesh control without any split faces. And you can see by looking at the size of the elements, there's a lot more elements here. And with the local mesh control, you can simply just refine the mesh in the area of interest and then with a smaller mesh count. And this is beneficial when you have 3 or 4 hotspots. So local mesh control is a great tip to make these solutions run faster. Now this one is a little bit more tricky to explain. Centroidal results. Now, by default, I should have done this the wrong way around, but it doesn't matter. I'll explain in a moment. So there is a document. I mean, if you're interested, let us know and we'll send you the document. Inside Nastran, there are 2 types of data. One is called corner results, and the other one's called centroidal. If you're using Inventor Stress as an example, then by default, it will be corner, and by default in Nastran, you are looking at the corner results. Now, what does it mean? So if I bring in the first results dialog box, can you see here? You can probably see my mouse. Can you see my mouse moving, Sid? Yeah, I think you can, yes.
Yep.
So by default, data type is set to corner. So centroidal. So what happens in the background, which nobody sees, is that when you look at the centroidal elements, then there is a value in each element in the middle. So this is some sort of a mathematical algorithm in the background. So this value of 7.647, for example, is the mathematical result. And when you plot the centroidal data maximum, then this is the value it's looking for when it displays. When you click on the probe, that is what the value it sees. It doesn't see that one, it's seeing the maximum value. These are the elements which are basically adjacent to one another. And then if you change it to minimum, you'll pick up the minimum value. And then by the average is the most common one because it takes the value. But in an ideal world, guys, if the element is small enough, all of these values should all be within 10%. So so you have three types of results you can look at. So when you plot your results, there are three different values. And what you're trying to achieve, in addition to your different mesh sizes, there is more data to look at to see if you've got the convergence. Now, the corner ones, same process. The corner ones are looking at the corner results. So this is by default what you see already when you look at your analysis. If you don't change it, that is what you're looking at. Again, the maximum value will pick up the maximum, it'll pick up the minimum, and also it'll pick up the average. Now, these corner results and centroidal results are absolutely useful when you get stress singularities, when you get a stress value which is way higher than what you are anticipated, then this corner values and centroidal values will help you a lot. I mean, what I tend to do is I look at all 6 values. If 5 of the values are all within 10% and then get one value which is way above it, then I will use the average of them 5 values as my result and ignore that stress singularities. Okay.
So just a quick question there, Wasim, in the chat is, my understanding was that the mesh refinement was to aim to converge centroidal and corner values to within 10%. So this is in reference to that slide you showed earlier?
Yeah, so basically when I ask everybody to refine the mesh, then that is irrelevant of whether it's corner or centroidal. So that will just change the mesh 3 times, and then this is additional that you can check and see what the values are. So this is an additional sanity check, basically. Okay, we can go to it afterwards anyway. Okay, yep. So right, so and then this is what I was trying to say. In the ultimate ideal world, you should be looking at, if you were to ask me which one is accurate, well, they should both be the same. Actually, it should be within 10%. That is what we are trying to do. So basically, this is in addition to your mesh refinement. Because when you're doing mesh refinement, you have to pick whether you're looking at minimum, maximum, corner, or centroidal, or average. So you have to pick them as well. So it's, by default, everything's set by average and corner. And this one, I think I use this a lot. When you have a very fine mesh, everyone, then by simply clicking on the averaging and no averaging is a good way to check that you have also received convergence. If the 2 plots don't look anything similar, then it basically tells you that you got to go and refine the mesh. So this is all telling everybody, these are extra tools and tips for you to basically have some sort of more confidence in basically getting your results. So this works fine unless everybody comes across with these. This is a hot topic, guys. It's a nightmare. It's very frustrating. Sometimes you feel like that. Sometimes you blame the software, it's not doing it. But stress singularity is not an Inventor Nastran issue. It's not an Inventor stress issue or any other ANSYS, for example, the other software. It's an FEA issue. Now, I will try my best to explain. You may be familiar with this example from one of the books. So stress singularities happens for various reasons. Now, the example you see on the screen is that if you apply a load on a point on the model, then that can also lead to stress singularities where you apply the load. Now, if you look at the stress formula, force over area, if the area of an element is almost very, very small, then you're going to get infinite stress. And that also basically gives you a stress singularity. And I think one of the tips I would suggest is never ever apply a load on a point or a small edge. If you need to apply a load on an area of a face, then I think we suggest that you create a split face using the split command. Split command is probably the most popular command for Nastran. So that's what I would suggest. But that one is not the most popular stress singularity when we do support calls. This is probably one of the more common ones. It's a cantilever snap fit. I've fixed it at the this side here, and I put a load on there, and then you get a very, very high stress on the edge of that cantilever. Now, and so basically, it doesn't matter what you do, the stress keeps on increasing. Now, if that happens, it may not happen in real life because that snap fit is attached to something else. So what I would suggest you do there is consider attaching it to whatever part is attached. I don't care about what the part is when it's attached to, but when you put a separation contact or sliding contact or whatever, or a weld or whatever, then the stress may not be as high as that. So when you do single parts, this is one of the most common stress singularities you will achieve. So this is one of the benefits, is to do it as an assembly, because when you have an assembly, you're adding flexibility and you're not adding rigidity in the model. So this is probably a harder one to fix. And then this one is another common one. When we start simplifying geometries and start removing chamfers and fillets, then if there is a sudden change in geometry from a horizontal to a vertical, for example, or vertical to horizontal 90 degrees, then you're going to get high stresses. So the tip here, guys, is keep the features in the geometry if it's in the load path. Load path basically is, if you don't show what it means, is that where it's fixed and where the load is applied. If there's a feature in there which you are suppressing, leave it in there. So do not basically suppress fillets. The reason why we do it is we want to simplify it so it runs quicker. So this is the stress singularities, guys. Now, obviously, it may not be so obvious for some of you. So what we're going to do here is we're going to take the most simplest example I can think of. Now, you can try this in any FES software, and I will guarantee it will never converge. Now, one question I would like to ask everybody, and you could put a response in the question, is how many of you use the convergence tool inside Nastran? Just put yes or no or something, then it gives us an idea if anybody is using it or not. So this is, when I used to do training a long time ago, this is an example I used to use. It's not a limitation of Nastran, it's not a limitation of any FES software, because there is sudden change in geometry. So this is ideal for a lot of our customers who do fabrications, steel work. If you have a sudden change in geometry, you're going to get stress singularity. So I'm going to basically give you some ideas of how you could basically get it to converge. So change the mesh 3 times is fine, provided it converges. If it doesn't converge, then it gives you more frustration. So let's have a look.
So there's a mix of answers there, Wasim, but mostly people are not using it.
Okay, well, good, because I was going to tell everybody not to use it, because it makes no difference. It doesn't work. That's a bit of a blunt statement from me, so please don't share that with Autodesk, but I don't think it ever worked. Okay, so what I've got here is a simple example. I have fixed it on, it's a cantilever there. You can see it's fixed on this face here, and I've put a load on this face here. Okay, so, and then I have picked a default mesh size of 3. So, and it's marble steel. So the yield limit is around 300, not 300. What is it? I'm not sure. I can check from here. It's 207. Okay. So I have run it already, so I didn't want to sort of take too much of everyone's time, because I have something new which I want to talk about, and I'll probably expand on that. But when I look at the results, so metals don't tend to fail under compression. So the most critical stress value I will recommend everyone to look at. Okay, bond meters is highly accepted in the FEA world, even in design code and everything else. But I would suggest you look at max principle. This is the tensile component, basically. So you can see here the maximum stress is along there, on the edge. It's trying to stretch, it's trying to bend. So okay, that's fine. So based on my recommendations of 3 millimeter was mesh size, I'm going to apply a global mesh size and say, right, let's go and have a look at the next one. So I'm looking for a stress value within 10% of 194, so less than 220. So if I go into here and click on display, and it goes to 270. So this is where frustration happened. This is day to day, guys. Okay. So now I get 270, look at max principles. Okay. So then I hope, let's try the third one. So with the third one, what I did was here is I did not change the global mesh size. I simply basically put a mesh control on the edge. You can see here, I put the edge along there, and I said make it half, well, less than half of 1.5. So when I go down here, and then also what I did here, just a little tip, I think everyone's familiar. When you put a local mesh control on in mesh settings, you tend to change this here. By default, that is set to 50% growth rate. So I've made it 1.1, so that when I put a small mesh size on the edge, then it grows by 10% until it gets the global mesh size. So when I look at the results here, let's have a look. What do we get now? Okay, 475. So here, let me say, well, what do I do here? Now, just a question on the, does many people have stress similarity issues? I guess that's why here in the webinar, just sort of say yes, no, just give us an idea. How's it looking, Sid?
Mostly yes. I'd say about 95% yes.
Fantastic, because the next bit is going to be right. This, so we have so the next one I'm going to spend a little bit of 10 minutes on. We may not have any time for questions, but are you answering any questions as we go along, Sid?
Yeah.
Okay, right. So because we've got Nastran, everyone, and I have two choices here. But let me give you the most common choice. So when you were to give this to a consultant or a third-party person, because obviously we are not comfortable with it, or maybe your experience will tell you, no, that's fine. You come a phrase called localized yielding or plastic yielding, that type of thing. What's basically happening is that when this component goes into service for the first time, it may experience a high stress, but it's not going to deform it, and it's not going to affect its structural integrity. So how do we basically come across what is this localized yielding? So what I've done here for everybody is I'm going to run it as a non-linear static analysis. Okay, guys, we do this as a part of our non-linear training course as well. But basically what it is a very, very simple setup. So you create a new non-linear static analysis, and then you get some extra. It's the same load and it's the same constraint. The only thing you have to change, which I have already done, is if I go to mild steel, right, this is the only thing you have to change, everyone, is you pick up the nonlinear button, and then you have 4 choices. So by default, when you do it for the first time, it'll be set at none. You click plastic, then you have the 2 rows, 0, that is very low strain, 207, and then the only thing you have to add is put 0.1, that's 10% strain. I don't expect that. and then put 207. That's the only thing you need to specify. The stress value stays the same. The strain value, put it as 0.1, 0.05, and then when you click on this one here, that is the only thing you'll see. So when the stress goes beyond 207, and this will get confusing, when you do nonlinear, it does not look at the corner values or the corner data. It always looks at the centroidal data. That's what it's doing. Okay, so when you think, well, it's not given, if the stress value is not going to be higher than the yield, in the corner it is, but in the centroidal it isn't. So if that's the case, then you're not going to get any strain. So if you want to look at the results, something's happening, look at the centroidal. So that's the only thing I've changed, or one of the things I've changed. Right. So the other beauty of it is that, can you see in the subcases? So I have got two subcases. You can right-hand click on there and click on new. That's what it is basically. The first subcase. Now you might be very curious, but don't do it. When you go on the nonlinear setup, we explain this on a training course. Don't make any changes, guys. Do not put anything in there. If you want to learn more about this, you can want the help, and definitely don't go in there and start changing that. The only time we come across and change that is when we have issues. So what I'm trying to say is there is no changes to make. The only thing you change is the material to plastic. You copy the first subcase, and what you're simply doing here is load one copy. The only thing you change, guys, is that you put a load of, obviously you need to put a load. I put 1 Newton. It's like having no load on there. So what I'm trying to say here is that when you put a load on this cantilever, the second subcase will start from the first subcase when it finishes. And then, what you're looking for is, I want to look at the deformation of this component as a result of that load, and also the strain value, which we're trying to establish, so that we can exclude these high stresses. Okay, so if I now go to my results here and click on display. Okay, so which result is it looking at? Well, if you look up here, that's the result at the end of my first subcase. And you see here, you may not be able to see this. Probably, I'll do it from here. If I click on displacement, so there you go. That's the displacement value, and you can't tell whether it's whether that is permanent deformation, or whether that's a deformation applied by the load, or is it a vibration, or whatever it is. But typically, I'm going to assume that's the deformation. But then if I then go into my second final subcase here, now what you are now looking at, it's going to be permanent deformation. And this is in millimeters, everyone. So what you can see there, there's no permanent deformation. So that's a good sign. So when you put the load onto there, you know for sure that there's no permanent deformation. But when you're looking at strain, when you're looking at these non-linear results, I'm looking at the strain value here. And you can see there, guys, this is what we refer to as localized yielding. And that value there, you times it by 100, and it's way below 0%. It's probably 0.01. So what I'm trying to say here, guys, is the high stress value you're getting, you can disregard it. So you can basically run the analysis as a nonlinear. Maybe you might want to do this, or maybe not. So if you think this is too much, then there's one more option, probably an easier option. But I think this is what refers to as localized yielding. So, for example, if you have inventor stress, then you may not have access to nonlinear. But I think 90% of our customers here are Nastran users, and they will have access to nonlinear capability. It's very easy, guys, to set up. But I'm going to try something different. So I'm going to go back and activate the first study. So we're back to square one again. I'm going to go into here. Now, this is basically the finished product. So my technical term is a fiddle, whatever you want to call it, guys. Now, I'm going to put a fillet size in there. Now, the fillet size has to be not too big, Not too, if it's too small, it may not converge, but it has to be such that it does not affect the structural integrity. What I mean by that is stiffness. So if the displacement is the same as having with the fillet or without the fillet, then it's a good idea. Okay, so if I go back to my analysis now, and I'm going to look at the results first to see, even though I've changed the geometry, if you don't update the mesh, the results will be the same. So if I go and right hand click on my displacements. Okay, now this happens, guys. Why is it not showing my results? Every time you come back from Inventor, you have to right hand click on results and click load. And then I'm going to click on displacement. I want to see what the displacement value is going to be. Can you see it? It's about 0.46 mil. Okay, that's fine. So now I'm going to generate the mesh to include my fillet. I'm going to run the analysis. And what we'll see here is I want to see a stress value. So we had about 194 or something now. So, and what I love about Nastran, I'm not sure if this happens to you guys, is, you know, when you run the analysis, does anybody get 0 warnings? It's a nice feeling. When you, yes, I know. Sid smile. Start putting contacts in there, but do not try to keep doing something on Nastran to get 0 warnings. They're not critical. Now you see there, I have 242, and the stress value max principle is on the bottom of the fillet. So that's fine. We'll stick with that. And if I then go to my next study, generate the mesh again. I better make a note of this. 242 was it? And then we run this again. This is one of the reasons why I put a very simple example so we can run it live and you can see it. And I'm hoping it's within 10% of 242. And also, right, okay, we're getting there. Okay, 242, 288. So we're getting there, we're getting close. It's on the borderline approximately. And then we'll try the last one. Now this one, because the last study had a mesh control on the edge, I've got 2 mesh controls here. So I'm going to go to mesh control 2. I'm going to pick the face, and then I'll generate the mesh again. So 242, 288. So run it again. So this is your second options to get convergence. Okay, let's see what happens. I'm happy that we 288, 10% of 288, 20. So we are within the last 2 are definitely within 10%, and you are more than welcome to go and refine the mesh again and see what happens. So for stress singularities, provided it's to do with a geometry change, then you've got 2 choices: run it as nonlinear static or put a fillet in there. Okay, so let's go back. What am I doing? Okay, so there you go. So run as a nonlinear or consider applying a fillet. That's what we've done. We've already done that. So, well, I hope it's given you some sort of ideas of how to sort of cope with the stress singularities. I hope everybody here has learned something new. I hope the nonlinear stuff was something new at least. Or perhaps you got lots of more questions. So we've got about 5 minutes here, so we could basically go and wait, see if you get any more questions.
So there were a few good questions there, Wasim, especially around the stress singularity, where somebody did mention that can you add in a radius to increase the area and simulate the stress distribution that way. So I suppose it's more around not having to use the nonlinear static analysis and essentially just put in a fillet and yeah. Well, there's an interesting question here as well. When will AI take over? So
The AI will take over the world, guys. Yes, it's happening, but not. It won't be happening in Nastran, but I guess it'll happen in other FEA software which are being developed. So we are seeing a lot of AI coming in other FEA softwares. Maybe Fusion. Fusion is probably the FEA product with the promoter deck, which is heavily developed. So maybe see something there.
Also, just so that everybody's aware, we will be sharing the recording with you guys after the meeting. So in case you've missed out on anything or you need to share it with your colleagues, it will be sent out to you. Yeah, I think other than that, mostly you have thank you messages, and yeah, looks like that's it.
Well, thank you very much, Sid, and again, thank you very much for your time. So just one last thing from me and Sid is that if you have any further questions, or is there anything in the presentations, perhaps the nonlinear bit, or anything around stress similarities, any tips, any suggestions, or any application you are doing at work, you would like to discuss it, if it's in confidence, then by all means send me or Sid an email. We could then try to find a time slot to book a 30-minute meeting to discuss the application or anything, any questions you may have. If you're or get in touch with your account managers, and between us, we will set up some time with you guys. So it's an opportunity for you guys to come and talk to us. Probably talking to most of you already when you have support. But I think it's just an opportunity to, if you want to learn more about the non-linears, then sit here. We do have scheduled course on that one. Have a think, but I think Philip is probably by far the most easy option, but the non-linear is also a very, very quick, accurate way to basically check your stress similarities. It's not going to go away, guys. Stress similarities is there. It's just the way how to cope with it. I think it's probably more difficult when you are new to FEA world.
Just one thing there, Wasim, there's a comment there that says you have to refer to recognized standards for the evaluation of the stress. I am not sure if that's a question or just a comment.
Say that again, recognized standard.
Yeah, you have to refer to recognized standards for the evaluation of the stress. So I assume this is referring to the von Mises and the max principle stress.
Yes. And also, when you're looking at standards, then they're also looking at a factor of your von Mises. So I don't know, 70%, 80% elongations. Yes. So yes. So depending on what stress value, I think von Mises is the most relevant one. But I personally look at the max principle stresses as the worst case scenario. For example, when I'm doing fatigue analysis, I look at the max principle. But yes, I hope that answers your questions. If not, then we can take it offline and then the meeting if it's a little bit more detailed and complex to understand. But I hope I answered the question to some degree.
Yeah.
Is there any more questions?
No, I think
okay, well,
that's it.
Okay, we're on time. Well, first of all, guys, thank you very much for your time. I appreciate that you are very busy. I hope this was very, very useful for you guys, and I'm sure we'll speak again at some point this year. Thank you again, guys. Have a great day.
Thank you very much, everyone.